Have you ever written some code and just scratched your head wondering why searching for one tiny thing in a massive list takes forever, but doing the same thing in a dictionary is instantaneous? Well, it's not magic. And in this explainer, we're going to pull back the curtain on the brilliant engineering that makes dictionaries one of Python's most powerful tools.
It all starts with a feeling every single developer knows. You've got a massive list, maybe a million usernames, and you just need to check if one name is in there. The code looks simple enough, but you hit run and you wait. And you wait. That feeling of, why is this so slow? That's the mystery we're going to solve today.
Okay, so to really appreciate why dictionaries are the answer, we first have to get up close and personal with the problem itself, the painfully slow, step-by-step way a Python list has to search for anything.
So let's look at what's actually happening under the hood here. You ask Python, hey, is John in this list? Python has no shortcuts. It has to go to the very first item and ask, are you John? Nope. Okay, how about you, the second item? Are you John? Nope. It has to do this over and over and over again. Now, with 10 names, who cares? But with a million? Your program is literally checking a million names one by one. This is what we call a linear search. And here's the crucial takeaway. The search time is directly proportional to the size of the list. If your list gets twice as big, the worst-case search time gets twice as long. It just doesn't scale well, and that's a huge performance bottleneck.
So, how do we break out of this linear trap? This is where the dictionary comes in. And honestly, it feels like it's cheating because it doesn't search at all. It does something much, much smarter.
Now let's try this again with a dictionary. You ask, is John in this dictionary? And bam! The answer is immediate. It doesn't matter if there are 10 names or 10 billion. The time it takes is pretty much constant. Why? Because the dictionary isn't searching. It's performing a quick mathematical calculation to jump directly to where the answer should be.
Think of it like this. A list is a notebook with no index. To find a name, you have no choice but to flip through every single page one by one. A dictionary, on the other hand, is like a notebook with a perfect index. You don't flip pages, you just look up the name, find the exact page number, and jump straight to it. So how does Python know what page number to jump to? Well, the secret sauce is a process called hashing. Hashing is just a special, consistent recipe that takes a key, like the word John, and instantly turns it into a number. And that number is like the page number. It's an address that tells Python exactly where to store and find the data associated with John.
The whole thing works in 3 simple steps. First, transformation. Your key, John, gets converted into its unique hash number. Second, mapping. That number is used to pick a specific storage slot in memory. And third, the magic step, retrieval. When you need to find John again, Python just reruns the exact same hashing recipe, gets the exact same number, and jumps right back to that slot. No searching required.
But for this whole instant jump system to work, there are some really important unbreakable rules. If you break them, the entire system falls apart.
And the biggest, most important rule of all is this: dictionary keys have to be immutable. Now, that's just a computer science term for unchangeable. Once you create a key, like the string John or the number 42, it's set in stone. You can't alter it.
Python is a strict enforcer of this rule. If you try to use something that can change, like a list, as a dictionary key, it's just not going to work. Your code will crash with a type error. Python is basically telling you, hey, I can't create a permanent address for something you might change later.
So why is this rule so critical? Well, it's to prevent a bizarre situation I like to call ghost data. Imagine for a second you could use a list as a key. You store some data with it. Then later, you change an item in that list. The next time you try to look up that key, Python runs the hash recipe on the new changed list and gets a different address. Your original data is still sitting in memory, but the map to find it is gone forever. It's a ghost.
So here's a quick cheat sheet for what you can and can't use. Your basic types, strings, integers, booleans, they're all immutable, so they're perfect keys. On the flip side, things that are designed to be changed, like lists, sets, and even other dictionaries, are a big no. And then you have tuples, which are the special case. They're okay, but only if every single item inside the tuple is also immutable.
All right, so now that we know the rules of the game, let's get to the fun part, using this knowledge to write some seriously elegant and efficient code. This is where we go from just using dictionaries to really thinking with them.
Check this out. Instead of writing a big, ugly chain of if, elif, elf statements to handle different commands, you can build what's called a dispatch table. You just map a command string, like save, directly to the function that should handle it. This code isn't just faster, it's way cleaner and so much easier to add new options to later.
Here's another game changer, especially for counting things. You know that annoying bit of code you always have to write to check if a key already exists before you can increment its count? Well, with a default dictionary, you can just stop doing that. The first time it sees a new key, it automatically creates a default entry for you, like the integer 0. It completely removes a whole category of boilerplate code.
And finally, let's talk about a couple of common traps that are super easy to fall into, even for pros. Knowing how to avoid these will make your code way more robust.
The number one mistake is the key error. If you try to access a key that isn't in the dictionary using the square brackets, your whole program comes to a screeching halt. The safer, more professional way is to use the .get method. It does the same thing, but if the key isn't found, it won't crash. It'll just politely return a default value that you provide.
Okay, this one trips everyone up at some point. You cannot change the size of a dictionary while you are looping over it. If you try to add or delete keys in a for loop, Python gets confused and throws a runtime error. The fix is so simple. Don't loop over the dictionary itself. Loop over a copy of its keys. That way, you have a stable list to iterate through while you safely modify the original.
So let's wrap this all up. What have we learned? First, hashing is the secret weapon. It lets dictionaries bypass searching entirely by turning keys into memory addresses for instant access. Second, that whole system relies on keys being immutable. It's non-negotiable. And third, all this incredible speed is the result of a smart trade-off, using a little more memory to gain a ton of performance.
If you walk away with just one single thought today, let it be this one. Lists, search. Dictionaries, jump. One plods through the data item by item, the other performs a calculation and lands exactly where it needs to be.
And really, that insight changes how you think about code. It elevates you from someone who just writes code to an architect who understands performance. So the question I'll leave you with is this. Now that you know the secret, where in your own code can you stop searching and start jumping?